I want to make a few remarks on this definition. So maybe first of all on the tensor product. So if, in particular, so if we know a basis, an orthonormal basis for our Hilbert space, let's say H, then of course I can also write down orthonormal basis for H tensor H. Of course I can also do it for H1 tensor H2, but let me only do it for the case in which we are really interested. So where I take tensor powers of one Hilbert space and assume that I have an orthonormal basis. So let me call it EI. So where I is running, let's say, from 1 up to D, where D is a dimension of my Hilbert space, and D can also be infinity. So I can also have an infinite dimensional Hilbert space. So assume EI is an orthonormal basis of H. So this means the EIs all have length 1 and they are orthogonal to each other. So if I have this, and D is a dimension, of my Hilbert space, and this can be a natural number, but it can also be plus infinity if I have an infinite dimensional Hilbert space, which we in many cases have. And then I'm claiming that we can also write down an orthonormal basis of H to the power n, and this is just given by taking all possible combinations, tensor combinations, between elements from here. So then I'm taking just E I1 tensor E I2 tensor and so on up to tensor E I, and okay, if I want to look on the Hilbert space to the power n, I need here n of them, where of course the i's are here running over all possibilities which I have here. So all of them are between 1 and D, but there's no order. So I mean they can, so each of them independently can run from 1 up to D. So I1, I2 up to In is less than D. If D is infinity, this just means they are just all natural numbers. So then I'm claiming that this is actually an orthonormal basis of the nth tensor power of H. So this is our orthonormal basis of H to the power n, which is very easy to see if you just use this product formula. So if you take a product of such a guy with another guy of this form, then the inner product is just given by pairing here the first term with the first term here, the second term here. So actually all of them must be the same. And if all of them are the same, you get 1 times 1 times 1 for the inner product. So the length is also 1. Yeah, okay, so this gives me a basis. And of course, now I can read off how many elements do I have in the basis. Of course, this is just D to the n. So this also gives me the dimension of the tensor power. And of course, this is multiplicative as it should be. So in particular, so this tells me that the dimension of H to the n is just the dimension of the Hilbert space H to the power n. Which of course means if H is infinite dimensional, then the tensor powers are also infinite dimensional. Yeah, so that was the first remark on the tensor product. And now maybe a remark on the direct sum, and maybe also comparison to the tensor product. Because I mean I defined a direct sum actually for infinitely many number of Hilbert spaces, but a tensor product only for a finite number. So one might also think, shouldn't I be able to define a tensor product of infinitely many Hilbert spaces? But let us think a little bit about this. And so first of all, this direct sum of my Hilbert spaces I can think of as the limit of taking just a sum over finitely many. And this is possible because I can in a clear way embed the sum of n terms into the sum of n plus 1 terms. And why can I do this? Because I can add the 0 in the n plus first component, and this shouldn't add anything. Because I have a 0 in a Hilbert space, and every Hilbert space has a 0, a unique canonic vector 0. So I can add this vector, and this means I can embed the direct sums into each other. And in this sense, I can consider all the HIs as also as subspaces of the direct sum, as I pointed out here. So okay, let me write this down. So since each HI has a 0 vector, and of course this is unique, so it's clear what the 0 is in a Hilbert space. But this means we can embed direct sums with a different number of summands into each other. We can embed direct sums into each other. So this means I can consider, if I only take a direct sum of the first n Hilbert spaces, I can identify this with a direct sum of n plus 1 Hilbert spaces, where I'm adding here just to 1. So this is the same, isomorphic to taking h1 plus hn, and then adding here in the n plus first component always the 0. The 0 of the Hilbert space hn plus 1. And then this is of course a subset of h1 plus h2 plus hn plus 1. Okay, so I can embed all those Hilbert spaces into each others, and then I can also see or understand the direct sum of infinitely many as a kind of limit, or a completion of all the finite ones, where the finite ones are sitting inside each other according to this. So the infinite direct sum can be seen as the completion of all finite ones. Completion of all finite ones. So I can also see the direct sum of the HI, where I'm running here over all the infinitely many. So this I can see, this is the union of the finite direct sums of the HI, where I'm only taking the sum of the n first of them, but then I let n run. So I take all the union of them, and of course this is not yet complete. So because this only gives me in this language, this only gives me sequences where I have only at a finite number of positions I have terms which are different from 0. So I still have to take the completion of this with respect to this canonical norm. Okay, but so in principle that's what I'm doing here. So if I understand a finite direct sum of Hilbert spaces, essentially I can go to the limit, and by completion I just get the infinite sum. And so maybe you might think that for the tensor product I should also be able to define in the same way an infinite tensor product of infinitely many Hilbert spaces. But then you see the problem is now what I need would be an embedding of a tensor product of n terms into a tensor product of n plus 1 terms. And of course, in the additive case for a sum, I can use the 0 for this. In a multiplicative case, I should use a 1 for this, but the Hilbert space has no 1. At least there is nothing canonical. There's no canonical 1 which I could use. So this means there might be a possibility by choosing some elements, but there's no canonical choice, and this means there's no canonical infinite tensor product for Hilbert spaces. So maybe I just want to write this down here. So there is no canonical one vector in a Hilbert space. And this means I cannot really embed tensor products of n factors into tensor products of n plus 1, and then I cannot say, okay, I take the infinite tensor product as the limit of this and maybe the completion. So since there is no canonical 1 in Hilbert spaces, so no embedding, so no canonical infinite tensor product. Yeah, and actually, I mean, at the moment we don't need this for our Fock space construction. We don't need infinite tensor products. We only need we need them for each n, but we don't have to embed those guys into each other because in a direct sum they are orthogonal to each other. Yeah. Okay, but actually the question about the equivalence of the CCR relations for an infinite number of degrees is actually very much related to this problem here. So namely, in the next lecture, we will address the fact that there are many inequivalent representations, and actually this corresponds to the fact that there is no canonical choice of an infinite tensor product, but we have actually many choices which we can make rigorous, and those correspond to situations which are not equivalent to each other. So we will come back to this question. I mean, at the moment we don't need this infinite tensor product, but I just want already to point out at this point here that this will play this question will play a crucial role in order to understand why we have many inequivalent representations of the CCR in the infinite dimensional situation.